Hey everybody, good morning, good afternoon, good evening, wherever you are. We are in for the second workshop of the WeTransfer Educate Series. The topic is Introduction to IPFS and Crust. We have a very special speaker, Brian, who today is going to be handling the workshop. But until then, let me just quickly say hi to all of you. GM in chat, feel free to say where all of you are coming from. Introduce yourself, use the chat for any upcoming questions that you might have, this is going to be yet another lovely workshop today. Let me just quickly have a look. We have Brian here in the audience already. I will quickly add him on stage. Give me a second. And while that is the case, I will quickly also announce that the workshop's already running. So everyone in the Discord that has not yet joined will be able to do so. Love to see you again, Brian. Welcome. Just before we start, I wanted to share a couple of interesting links with all of you, links that you have all of you already known, but I just want to make sure and reiterate all of them with you because they will be really useful for the Educate series. The first one being our Notion Hacker Pack, which includes every single important bit that you might ever be in need of for the duration of the program, which includes recordings of all of these workshops, as well as information on all kinds of resources that will come in handy. And they will come in handy because unlike all the other Educate series, this one includes a very special bounty as well. So we encourage all of you, apart from taking time to be in all of these workshops, to also try and build something towards the end of it. We'll have a dedicated 2 weeks of building where you will be able to compete, depending on what you end up building, for a prize pool 10K provided by the Apsilon team. If you're looking for someone to build with, please make sure to fill in this form. This form will be a few questions that will mostly collect information on what your background is, what your previous experience is, and it will make it as easy as possible for everyone that is also looking for a team to kind of reach out to you. And if you are someone that would like to look into people that have already listed their profiles, feel free to use the link that I'm sharing right now. It is basically a board with applicants and developers that are also looking to find someone like-minded and build something interesting for the Educate series. But enough about me and links. Welcome, Brian, once again. And I'm very interested to start the introduction to IPFS and Crust. How are you doing?
Yeah, thank you, Yasin, and thank you, Eagle Club, to coordinate events. Yep. So get started, or should stay away for a few minutes?
Sorry?
Get started, or should wait for a few minutes for the audience to join?
Yeah, feel free to start. The event is already running and everybody is joining in by default. Any questions, everyone, please make sure to voice them in chat. Brian and I will be having a closer look and there will be a dedicated Q&A session at the end. Feel free to also use the question tab on your bottom right if you want to post any questions based on what Brian has to present. But yeah, without further ado, Brian, feel free to share your screen and yeah.
Yep, start. Can I see the screen?
Yes.
Okay, I get started, right?
Perfect, yes.
Okay, thanks, Yasin, and thanks for Eagle Club to coordinate these events. And good morning and also good afternoon, good evening for all the audience across the world. And my name is Brian Wu, the core dev of the Crust Network. Today I will have a brief introduction for the Crust Network, the decentralized storage solution for the Web3. And we will divide today's sharing into 5 parts. The first one is the Crust Network introduction and overview. And part 2 is the technical stack introduction, including IPFS, the MPOW, the GPOS, and so on. Part 3 is the product introduction that builds on the Crust Network. Part 4 is how to build and develop with the Crust Network SDK and API. The last part with the Q&A section. Okay, let's go to the first part. And Crust Network is a public blockchain network for the decentralized storage and also deploying solution for Web3 ecosystem. It uses the IPFS as the underlying storage protocol and expose instant accessible on-chain functions for the applications and users. Now the whole network has over 500 terabytes storage and over 1,000 storage nodes all over the world. Its permission is to join the Crust network to provide storage power and earn the CRU tokens as rewards. The more nodes we have, the more decentralized it is, and also the more trust it is. And the Crust mainnet blockchain builds on top of IPFS, the storage proof module, the blockchain consensus module, and the storage market module. It provides comprehensive SDK and API and products for both the Web2 and Web3 ecosystems. And the Crust network can be used in a wide range of scenarios, including the DApp hosting, NFT storage, and trusted storage. For DApp hosting, Crust can provide better security for DApps and prevent issues like DNS hijack and downtime. For NFT storage, Crust can provide guaranteed and verifiable storage to ensure the NFT contain content ownership and persistence, and so that you may not lose your NFT, which may worth over $1 million in the future. And for the trusted storage, it provides the trusted and, more importantly, the auditable trust on technologies, including like sensitive data like KYC documents and accountable data like the carbon footprints. Okay, and Crust network has integrated with the most popular Ethereum-based chains and Polkadot-based chains, like Ethereum mainnet, Arbitrum Optimisms, or the Moonweaver and A-Start on Polkadot. And also, we have a large amount of users from different Web3 domains. For example, in DApp hosting, the Uniswap and AV has deployed their website front ends on Crust, and NFT storage like NFT Scan, Kaka, NFT World, and UniArts are our users. And there are many more other users in the general Web3 storage domain. Crust network also has built up a big ecosystem right now with over 150 projects and partners, and is continuous to onboarding new users and partners. Okay, that's the brief introduction for Crust network. And now let's have a deep dive into the part 2 for the technical stack we are using right now in the Crust network. Crust network works in 5 layers as described in this diagram. Let's see from the bottom up. The first layer is the IPFS, the interplanetary file system. This is the underlying storage engine and protocol that for Crust network. We have customized the IPFS protocol to fit in the Crust network requirements. And the second layer is the MPOW, the meaningful proof of work. And since its permission is for any physical servers to join as a miner to provide storage power, we need a zero trust storage proof layer to inspect and prove storage work of the miners to avoid any cheating or scamming. We use the TEE, the Trusted Execution Environment technology to do the proof of the work. And the middle layer is the GPOS, the Guaranteed Proof of Stake. This is the POS-derived consensus layer that requires nodes to provide a storage proof to get a staking quota. GPOS is the mechanism that a miner can get CRU tokens as rewards in a fair manner. The one who provides larger storage volumes and store more files can get more rewards. It's built on top of the substrate baby and grandpa algorithms. And this layer is the DSM, decentralized storage market. It maintains a storage order pricing and rewards mechanism and enable users to place orders on a chain, which can then get their data stored and distributed across the network. The top layers are the products built on Crust network and SDK, which we will talk about in details in Chapter 3 and Chapter 4. Now, let's go to the first part. Let's see, what is IPFS, right? The Interplanetary File System. It's a decentralized storage and delivery network which builds on the fundamental principles of a peer-to-peer networking and content-based ajaxing. In traditional client-server HTTP model, it is centralized, right, and which all users access a single server data center to get data. But for IPFS, it is a peer-to-peer model. No central servers, all servers are equal. IPFS has no single point of failure, and users do not need to trust each other, so make it more reliable than traditional systems. IPFS also eliminates the problem of link lock by allowing data to be addressed by its contents rather than by its location. This is the so-called content-based addressing. So in other words, content in IPFS is still reachable regardless of its location and does not depend on specific servers being available. So generally speaking, a basic IPFS workflow includes 4 parts between the content producer and the content consumer. First, the content owner imports or uploads the contents to IPFS through a local IPFS node or remote IPFS gateway. Then the content will be chunking and then distributed to different peers. The contents will have a unique identifier called the content ID, the CID in short, and you can alternatively give it an IPF namespace as its name. And when the content consumer wants to fetch the content using the CID, IPFS will use the Academia distributed hash table to find out where all the chunks of the CID are located. And then the IPFS nodes will use the bit swap mechanism to fetch all the chunks of the contents. And this diagram shows that a continuous file of contents will be chunked into the blocks. Right? Then each block or each chunk is hashed and will be distributed to different peers in the IPFS network. So here will be some questions. Right? Question number 1, how does these chunks link to the file's unique CID? And question number 2 is, what if I upload a folder with many files and subfolders inside it? So the answer goes to how IPFS is doing the content addressing. As you can see in this diagram, it uses a Merkle-derived acyclic graphs, the Merkle DAGs in short, which are graph data structures where each node is content addressed. This is kind of similar as the Merkle tree structures you can find in the blockchain, data tree, and state tree. This diagram shows that if you upload a folder to IPFS, how the IPFS will link all the contents inside the folder to the root folder CID. Each file and each subfolder will also have their own unique CID, and they are using the Merkle DAGs to link together. It's the same structure for the file CID and all its chunks. Each chunk will be hashed and also has its own CID and will be linked with the file CID in the Merkle DAG structure. And the file's Merkle DAG structure will be a subgraph of a large Merkle DAG if this file belongs to a folder. So with this mechanism, we can use the content-based addressing in IPFS, then the traditional location-based identifier in Web 2. You can see that a traditional HTTP web page URL here can be represented by fully by content address, as you can see this CID stream here. And when the consumer wants to fetch the file contents through a CID, the IPFS will use the Academia distributed hash table, named the DHT mechanism, to find the peers in the IPFS network which store the data you are seeking. The Academia DHT can be thought of as a large table distributed across many nodes that stores information about which peers have which data. IPFS used the libp2p framework to establish the connectivity between peers. This diagram shows an example of fetch data from the NFT storage link application. Right? When the user requests an NFT contents with a CID, the NFT storage.link replication will read the data from the IPFS network. First, it will reach out to multiple IPFS gateway for the content retrieval raising. The IPFS gateway has a local IPFS node running on it, which will use the Academia DHT and bit swap mechanisms described in the field slides to fetch all the chunks from each other nodes. When the IPFS nodes, local node on the gateway retrieve all the chunks of the contents, it will return back the whole consolidated contents to the user. Okay, so the previous slides are basic overview to the IPFS protocol. Actually, IPFS has more concepts and functionalities than what's shown here. Due to time limits, you can refer to IPFS official documents for more deeper information. This slide just shows some tools provided by the IPFS which can be used by any user directly without knowing any too much technical details of IPFS. For example, the IPFS desktop, it bundles IPFS Node, File Manager, PM Manager, and others into a single application. And the IPFS command line tools is command lines, which allows you to do everything you can do in a desktop, but you can incorporate this into your script automation tools. IPFS pinning tools, pinning service allows you to tell IPFS to already store a given CID. This is done by publishing the contents from a local node to other remote peers. And the next is the IPFS gateways. That's public service providing a bridge between the HTTP and IPFS, allows you to use the HTTP protocol to request data by CID from the IPFS network. And next is the IPFS, the companion browser extension, which allows you to access the IPFS apps natively through your browser. And IPFS SDK has provided in different languages like the JavaScript and Golang and the other languages. Okay, now let's have a look at the second layer, the MPOW, the Meaningful Proof of Work. MPOW is a Zero Trust Storage Proof layer. It is implemented based on the TEE, the Trusted Execution Environment technology. There are three major processes: the store process, report process, and verify process. As you can see in this diagram, this is the store process. Data is transferred to the Crust node through IPFS, and then it will use the TEE to seal and store the data locally. The second process is report process, the dark lines here. The node will use the TEE to inspect and assign a work report periodically. The work report includes incremental information of data storage work in this load. And then we will broadcast the reports onto the Crust mainnet chain. The third process is the verify process, where the on-chain logic will verify whether the work report is valid and then calculate the valid storage power for the nodes. Based on the TE technology, the nodes in Crust network can perform non-interactive low-trust storage proof. The MTU, this is a detailed look inside a Crust storage node. When the IPFS receives the file contents from the peer-to-peer network, it will invoke this program we call the S worker, which stands for the storage worker, to do the content sealing using the TEE. S worker will inspect, sign, and broadcast the reports periodically. The TEE is commonly known as an isolated processing environment in which the application can be securely executed irrespective of the rest of the system. There are multiple TEE solutions like the Intel SGX, ARM TrustZone, and AMD SEV. Crust Network used the Intel SGX as the TEE solution. And here's a brief diagram for the Intel SGX. The Intel CPU will create a special memory space called enclave, isolated from the operating system. The execution logic in the enclave is verifiable and tamper-proof, and the data in the enclave cannot be read or processed by any program outside. The enclave is considered to be credible as long as it is verified. Okay, in order to make the IPFS to work with the S worker to do data sealing and stealing, Crust Network has customized the standard IPFS protocol implementations. As you can see in this diagram, file blocks received by the IPFS will be sent to the S worker to seal and store. IPFS doesn't store the original file block anymore. Instead, it will store the file block index. Index, as you can see here, returned by the S worker. IPFS can get the original file blocks by providing this block index to the S worker. This part shows the details on how S worker is doing the sealing work, but we will skip this detail in this sharing. You can refer to Crust Wiki for more information on this detailed logic. And this diagram shows the content retrieval process. When a file block request coming, IPFS will send the corresponding block index to the S worker to do the unsealing, and then gets the real file block data back. And then it will send back the data to the requesting node. And now let's have a look at the middle layer, the GPOS, the guaranteed proof of stake. The GPOS is a POS-derived consensus protocol. Like the MPOS, the nominated POS, a user can vote to specific nodes, and we define the voting behavior as a guarantee process. The key difference is that each node has its staking quota, or say the staking limits, decided by its proven storage resource and work. Therefore, the GPOS encourages the nodes to provide more storage resource to take more work and improve the security and robustness of the network. The GPOS leverages the storage work reports generated by the MPOW storage proof to calculate the storage power. The more storage resource a node contributes, the higher stake limits it can attain, which means that if the node doesn't store enough real files, it will have a lower stake limits. Any balance over the stake limits is not effective when calculating the staking rewards. GPOS also encourages users to stake their tokens to high-quality nodes via the guarantee operation to attempt staking income. GPOS is based on the substrate framework. The block generation and finalization algorithm is the baby and grandpa. If someone wants to control this network or attack this network, in addition to having a large proportion of CRU tokens, they also need to control enough storage resource. Such design will make the attack more difficult in the cross network. Now have a look at the DSM layer, the decentralized storage markets. The DSM allows storage users to place storage orders on chain, and the files in the storage order will be stored by the cross network and the cross storage nodes. DSM contains three major mechanisms. The first one is the pricing mechanism. The storage order fee is calculated by network according to the file size, the storage period, and overall storage requirements and supplies. Two, the benefits and rewards mechanisms. The DSM market have multiple rewards and mechanisms to incentivize the storage nodes. Number three is the retrieval mechanism. The DSM includes another layer of incentivize to encourage the nodes to support data retrieval. The nodes providing better retrieval service will get higher ranking and have a better chance of getting more files quickly, thus getting more storage payments and staking income. The top layer is the products and SDK built on the cross network. This is a list of products and SDK. We'll go through this in detail in the next two chapters. Okay, we just have finished the cross network technical stack introduction. And now let's have a look at some of the cross network products we have developed. And the first one is the Cross Apps. This is an enhanced management portal developed on Polkadot.js apps. Except the normal operations that provided as the original Polkadot.js apps, we have added some specific features for cross network, like the CRU token bridge between different chains, the embedded storage features, and cross management features. Let's have a look at a real user interface. Okay, this is the Cross Apps. You can see that we developed it based on the Polkadot.js apps, except for the normal operations like the accounts, the checkbox is provided by the base Polkadot.js apps. We added like the bridge function here to bridge the with this function, we can bridge the CRU tokens between the cross network and Ethereum, or the cross network to L1. Also, this is the benefits and rewards module provided by the DSM markets. And here, under the network, the staking menu here, we can see that this is how it's controlled by the GPOS module. We can see 70 validators and 179 guarantors. And here, there's columns. Here, the power limits. That's what we call the staking limits. That is powered back by the storage proof of this validator. So the higher power limits, then you can stake more CRU tokens here. It can be backed by more storage resource and store more files. And then the other menus is for the governance and democracy, and so the developers menus for the chain on-chain state query and send the transactions in Polkadot. And here, these are the two menus that we add for the Crust Network functions, like for the storage user. And wait a second, it's loading, okay. And we can upload a file here through this user interface. Let's say we upload the Crust apps here, and we can sign and upload this. We'll upload this file to the IPFS gateway. Let me sign it. And actually, we get the CID from the gateway here. Start with the QM letter, and the file size is 26 bytes. And we will place the storage order to the Crust network to make it store on the Crust storage nodes. And this file price is very cheaper, just 0.001 CRU tokens. And let's confirm this and sign and submit this transaction. Okay, we are using the Crust wallets to place the storage order here. This transaction details. This is the CID, and this is the file size. This is the tips, and let's allow this transaction. Okay, the transaction is a success. We can see the files here. This is the file CID, and the expiration dates. By default, the file will keep for 6 months on the network if you do not put any money on it. There are 47 replicates in the whole Crust network, which means that there are 47 physical storage nodes have this file stored on it. And this action is the renewal, which means that you can place new storage order for this file to make it last for another 6 months. And if we copy the download link here and open a new tab of the browser, here we can open the file. We show the file through this IPFS gateway, and here we can see, right? Okay, so the source available. Maybe the gateway has done. We can change to another IPFS gateway. Let me show whether we can see this file. Okay, let's move on. Maybe something more with this gateway. And this is a renewal pool, which means that you can add a prepay file to this file to make it stay as long as the pool has balance in it. Let's say if you put 100 CRU tokens in it, as long as this pool has money in it, the file would be kept on the Crust network. Okay, you can also have the other functions like the Crust files we will talk about later, and the ping files that you can use this to ping the CID you already have. Okay, and the next one is the Crust files. Okay, it's a personal. This is the second product we will introduce. This is a personal web drive, like the traditional Dropbox or Google Drive. You can store your files in a decentralized and distributed storage network instead of a cloud server. That is stored on the IPFS and the Crust network. You can store your files for a period of time or permanently. And you can also store your files with end-to-end encryption. Also, you can share your files to friends with a link or by Twitter. You can write and down your stored files. Okay, let's have a look at these products. Okay, here And okay, let me log out first. You can you can log into this cross-file product using Web3 authentication. You can log in with the MetaMask or using Crust Wallet. Just log in with the Crust Wallet. Okay, it's loading. Right, here is it. You can upload and store files, okay, right, through this good user interface. And for the public mode here, you can upload the files to this section, and all the files here is actually public accessible, right? For example, we upload a file of the text txt. The content is the hello crust files. And you can pick IPFS gateway. These gateways, there's a list that Crust have deployed multiple gateways in many locations across the world. You can pick up the one that is close to you to have a better performance, and you can select a Web3 IPFS pinner, or you can configure your own IPFS pinner. And then let's confirm it, and we can get the files stored in the Crust network. And this one I've just posted, and this is the CID of this file contents. And we have 43 webcasts for these files. And we can open the file. Yep, for this file, right? This is the IPFS gateway, and this is the CID for this file. We can see hello crust files. And also we can share it with this link. You can just post this link to your friends or family, and they can access the file from this page. It's actually, when you click the open file, it's actually still the same. Get the files from this IPFS gateway, right? Okay, you can also create a tweet here, and then we post tweets with this share link. Okay, and for the votes feature here, it is used for the encryption file, which means that you first generate your encryption key here in the settings page. The keys is stored locally in your browser. No one have this key except you. Also, the server side doesn't have this key. So when you upload files through this feature, the file will be encrypted locally in this browser using the key you generated in the settings page. And then it will upload the encrypted files to the IPFS gateway and store on the Crust network. If let me copy this file CID. If we just query this file through the CID by the gateway, check, okay, save it, open that. As you can see, right, the file content is encrypted. If you don't have the keys, and if you don't open it from this user interface, you will get encrypted data. If the others all have this CID, we still cannot see what is inside this file. And so be aware that you have to keep backup your encryption keys. If you lose your keys, then you lose your file contents. Okay, that's all for the Crust files. And the next part is the Crust Cloud. Crust Cloud is a cloud storage solution like the AWS S3 storage beyond the IPFS and Crust network. You can create a Web3 bucket ID. It is an NFT. It's just like the S3 bucket ID. This W3 bucket NFT can be transferable tokenized storage buckets in various sizes and types. You can store and retrieve the files with this bucket ID with the W3 auth gateway and pinning service, just like you store and retrieve the files using the S3 bucket ID. Okay, the Web3 auth is a secure and customizable authentication system, which we will talk about this in the part 4 of this sharing. And check this Cross Cloud. That is the Cross Cloud main page. And if we launch the application here, okay, connect the wallets. Okay, this is my wallet, and we change to the Arbitrum network. And we can mint a new W3 buckets. And this is the size that you can choose: 10 gigabyte, 1 gigabyte, and 1 terabyte. And this is the money that you need to have this size of the buckets. We'll provide a smaller size like 1 gigabyte or 100 megabytes in the future. And then we will pick the 10 gigabyte one. The next step, this will call the MetaMask to sign the message. This will create the NFT for me. Okay, and you can pick up the color for this NFT, and you can continue to generate the metadata. This metadata will be stored on the Crust network. And okay, check. During this process, actually the backend will place a storage order on the Crust network, and the NFT metadata will be stored on it. Okay, I'm not going to continue this because I will not make the payments. Right? Okay, you can try yourself after this sharing. And this Crust IPFS scan product is a free and handy open IPFS Explorer application. You can enter a file CID and search. It will tell you how the IPFS stores the file, including does this file exist on the IPFS, how the file is available in different locations across the world, and how many records they store, and which node stores replicas. Let's have a check. Okay, this IPFS scan website. You enter the CID, and you can see that for this file, we have 50 replicas confirmed in the Crust network. And this file has the 6 months storage guarantee. And if you can copy the download link here, so that you can retrieve it via the file, the web browser. Okay, and also you can see these are all the storage nodes that store the replica of these files. Okay, so you can use these tools to check your file status across the Crust network. Okay, that's for the products part. Now the next part, the chapter 4, is how to build and develop with the Crust network. Before we go into the source code details, let's see how to let's see how the Crust IPFS Web3 Scaleway and the pinning service. We have added a reverse proxy before the standard IPFS Scaleway. It provides the Web3 authentication ability. Let's say, for example, in the client side, if you want to upload the files through this Scaleway, you first sign your public key with your private keys using any Web3 wallets like the Ethereum wallets or Polkadot wallets, and then you will get a signature. And then you can call the standard IPFS API with the basic auth header in these formats. And when the server side receive the request, it will pass the header and extract the public key and signature from the header. And if it validates the signature of the public key, if the validation succeeds, it will proxy the request to the backend standard IPFS gateway. Okay, and for the pinning service, after you upload the file to the gateway and have the CID, you can call the pinning service to ping to the Crust network. First, it will also use the same Web3 auth in the HTTP header as the Crust gateway service. And then the pinning service will place the storage order to the Crust network to make the files store and persist in the Crust storage nodes. The Crust pinning service will record and manage the on-chain status in its database, so you can query the file status through the pinning service API. And then part 2, let's develop with the IPFS Web3 gateway and the pinning service. You can find the source code on the official CrossGap report here and related wiki document on this link. Okay, let me open the file here. Okay, this is the Crust demo report, and this is the store file with Pinger. Let's just go through this source code one by one. These are just some standard library that you will need to require. The GOTS HTTP module, the standard IPFS HTTP client module, and the Polkadot keyring module. And then these are the basic inputs, right? This is the path that needs to be uploaded to the IPFS. And this you can pass in the Cs of your cards through the command line arguments. And this is the Crust IPFS Web3 or OST gateway address. And this is the pinging service address. The second step is to construct the OST header using the Polkadot keyring API. You can load the Cs and then sign the pair ejects with the to get a signature. And then this to construct the OST header in these formats. Here, the substrate here is the wallet type that you are using to sign your key address. We also support the other wallets like the Ethereum and other wallets. And step 3 is to create the IPFS HTTP client. This is a standard API of the IPFS. Pass in the IPFS gateways, URL and its API. And we put the authorization, the basic authentication OST header here. And then we invoke the add function to upload all the files under this path to the IPFS gateway. And then we will get the CID for the root folder. Right, and then the step 4 is to ping the Crust network with the pinging service. Here we use the GOTS library to post and request. This is the pinging service URL with the ping API. And we also use the same OST header as the bearer authorization header. And we put the CID and the name as the data body of this request. After we receive the response from this pinging service, we can query it for the ping status through the pings API with the request ID returned by the body, also the same OST header. So this typically just 7 lines of code that, to show how to upload the files to the gateway and also ping the files to Crust network. Okay, and this is the first way to interact with the Crust network. Another way is to develop just with the Crust storage API. We provide a Crust JavaScript SDK, and then you can just place the storage order using the SDK we provided. Let's have a look at this source code. Okay, we import more libraries than the other one. Right, this is the Crust IO and the type definitions that we provided in our SDK. And also this is the gateway, this is the endpoint for the Crust mainnet chain, and this is the gateway for the IPFS. And then this is the file contents. This is the file that we are going to upload, the Hello Crust Network 2024 as its content. And then we read the file contents into the program. And this we are creating the OST header using the Ether's wallet. We just create a random pair and then sign the message with the public key. Then we construct the header with this format. Now this is the OST type with the ETH. So now we create the IPFS client, also using the same IPFS gateway and the API with the basic OST header here. And we call add file. Actually, this function has the same API calling as the previous one. We call IPFS with the file contents, and then invoke the file state to get the status of this file, which contains the CID and the file size here. And then with the CID, we will place a storage order directly to the Crust network. Here for this function, we invoke the API to send a transaction to our storage markets. This is the place storage order function that we provided in our Crust mainnet chain with the input parameters of the file CID, file size, tips, and the memo. And now we are loading our Cs with the keyring Polkadot API, and then we are using this keyring pair to sign and send a transaction. And then if the transaction is success, then we will show it here. And now the next steps to add prepaid is optional, which means the renewal pool, we have money there so that the file can last for longer, 6 months longer. Okay, and this is also to get all the states from the Crust mainnet chain. This is also to invoke the API here to just query the states DB of the Crust mainnet chain. Okay, we can just have a quick demo here. Okay, and then if we run this program, here I just first upload the file to the IPFS web source gateway, and we will get a CID returned back by the gateway. And then the next steps to place storage order. The transaction is success, and we will also add prepaid success for this file. And there are 44 replicas for this file contents. Let's just copy this CID and let's try to get it. The file contents here. Okay, check. A little bit slow on my network. Let me try this gateway. Okay, here see we can get file from this gateway, Polkadot Crust Network 2024. All right, and then the next part is the how to develop with the EVM storage smart contract. Actually, Crust has developed an EVM storage contract which can be deployed into any EVM compatible chains. Users can then place the storage order by interact with this smart contract with any familiar tools that in the Ethereum world. There will be order merchants which will listen to the events published by this contract and then place the actual storage order on the Crust mainnet chain. And you can have a check the real source code here under the EVM folder, the is demo. And as you can see, there are a few parameters here. We just need the Ether's wallet here. And this is the API interface definition for that smart contract. And this is the contract ajax deployed in that chain. Please be aware that please use the official contract ajax published on the official Crust wiki to avoid any scam attack. And this is the chain URL of this ajax. And this is the private key you will need to change to your own if you want in your own space. And this file CID that you previously installed on the IPFS gateway, and this is the file size. So the first step is to get the provider with the chain URL, and then we get the signer with the private key. And now we create the this EVM storage contract instance here. And we just invoke this storage contract to get a price and place the order with the file CID and the file size. Just a few lines of the code, then you can place the storage order to the Crust network. Okay, due to time limits, I will not going to run this source code. And the next is the how to develop with the Polkadot XCMPs with the Crust parachain. This is the Crust parachain running on the Polkadot relay chain. For those who are not familiar with the Polkadot ecosystem, the parachain is kind of similar as the layer 2 chains in Ethereum world, like arbitrum and optimism. And other pair chains running in the Polkadot ecosystem can utilize the standard cross-chain communication mechanism in Polkadot, which is named XCMP, the cross-chain message protocol, to place a storage order request inside substrate package directly. So the Polkadot parachains can just build and integrate across decentralized storage capabilities fully on-chain. And this is a simple XCMP code snippet on how to place the storage order to the Crust parachain. This code is written in Rust language and is used inside a substrate palette. So the first line is a tuple for place order with this file CID and size specified here. And the second step is to construct the cross-chain message for this place storage call. And then the final step is to invoke the message sender to send this message cross-chain. The multi-location here specifies the cross parachain as destination for the message. And project is to develop with the cross command line tools. You can integrate these command line tools in any script automation. Okay, next, I have a quick look at it. After you install the cross CRI with the npm command, okay, here as you can see, right, npm install the cross CRI I've already installed. First step is to log in with your seeds. I already log in, so I skip this step. And now you can upload a file with the ping command with the let's say the cross CRI text here. Now it pings a sex with this CID. Okay, and now next step you can use the publish command to publish this CID to the cross mainnet and make it store on the cross storage nodes. Okay, here we'll connect to the cross mainnet chain. Okay. Oh, sorry, I can. Oh, the seeds is off dates. Okay, again, then we can skip this, and because I have no seeds on my hand right now. Okay, and let's go back to the slides. And the seven is to develop with the GitHub workflow and actions. And you can refer to this cross reports, the IPFS cross pinner, on how to use the published GitHub actions of the Crust. It will be quite easy to integrate those actions into your own report workflow. Let's have a look at the source code. Okay, here. This is the Crust Pinger report. And next, open the template workflow here. Next, the first step is to check out source code here. And the second step is using the cross IPFS upload action. You can upload any artifacts that is built from your report. And this is the path specified, and you can configure the cross Cs in the GitHub settings, secret settings. And the last step is to ping these files to the Crust network. By invoking the Crust IPFS cross actions. You can specify the CID which is coming from the second step, and with the cross seeds that you specify in the GitHub report. Okay, and go back to the slide. Okay, the last part is the Subscan Explorer. This Explorer provides a comprehensive functions to query and analyze the on-chain data. Let's have a quick look on it. And here is the main page of the Crust Subscan Explorer. You can see some statistics of the current chain status. And you can also query the data like the blocks, the transactions and transfer, transactions, events, assets, and account details across the whole chain. And you can see the storage statistics of the whole network with 1,000 storage nodes and over 2 million files are currently in storing on this network. Each file has average 32 replicas. And also the staking, the statistics for the whole network, the governance and the democracy of the network. Okay, and then let's go back to the slides. And that's it for today's sharings. And these are the official contact channels for Crust. Welcome to follow these links. Okay, so any questions from the audience?
Thank you, Brian. Yes, there are some questions. If you click on the question section
Okay.
on the bottom right, you will be able to review the majority of them.
Okay, yep. Okay, drink some water. Okay, next up. Okay, the first question is, in terms of the tokenomics, how can you ensure that incentivize to miners are enough, and also the storage price keep competitive versus the centralized alternatives? Okay, that's a big question. Okay, so actually we have designed as we in the decentralized storage markets, we have the benefits and rewards mechanism that we design to ensure that the miners can have enough incentivized to make them store files. As you can see, we have over 500 petabytes and 1,000 server nodes in the whole network. And because our incentivized mechanism can make sure that they can earn enough money to support their server operations and also earn money by staking more CRU tokens on its staking limits. Okay, and you can refer to the Crust wiki for more information about the tokenomics. You have more information and the details on how we do it for those the rewards and the benefits mechanisms. Okay, and the next one is the code for Crust file open source. Yeah, of course you can. All the source code is open under this Crust IO report on the GitHub. You can refer to this repository for all the source code. Here's the ping. It is the core source code. This is the source code for the mainnet chain, and this is the source code for the storage as worker, and these are management scripts for the deployment and management, and this for the API. This also deploy on the storage nodes. And this is the Crust apps that I just demo. And this is a storage manager. This is for the decentralized market implementations. Okay. And go back to the questions. And next is there some way for one-time payment to store data indefinitely similar to Lighthouse? If you want to store data indefinitely, right, you can just put, let's say, enough money here in the renewal pool, right? Let's say if you put maybe 100 or 100 CRU here, then you will make your files stop permanently because right now the storage price is really low. You can see in these statistics, the storage price here is just 0.003 CRU tokens, and each CRU token is just $1 right now, which means that you storage file just less than 1 cent. Okay. And the next is the IPFS node. The IPFS tools are not specific to Crust Network. Does it mean anything deployed to IPFS can be hosted on Crust Network? What exactly does it mean to build on Crust Network? Actually, here the IPFS is just a protocol. It actually doesn't have servers, right? You need to build the servers to implement to run the IPFS nodes. So the Crust Network is actually running the modified version of IPFS with 1,000 server nodes. So you cannot just use the IPFS to store the files. If you are installing the IPFS desktop, you will only have a local IPFS node in your machine. Right? There will not be any other servers you can use, right? So but for Crust Network, we are deploying all those servers, 1,000 servers that's with the IPFS protocol supported, and then we are adding the incentivized layers on top of the IPFS, so that you can place the orders and make it store on the whole Crust IPFS network with over 1,000 server nodes applicable to all these to the files you store. Okay, and that's why I'm building something called this my signed ID, decentralized doc sign, a document sign alternative. I wanted to understand how do I store image PDF that's only available to regular Metasic wallet. I think the IPFS doesn't relate to the file format. You can store any files onto the IPFS. That means that you can store any files onto the Crust network. So no matter it's a PDF or image or any other files, that you can just put it into the Crust network. Next is, can you talk about what features are available for Near? That is for the EVM storage, and we also have the smart contract deployed on that Near chain. You can also use the Near wallets to as the authentication methods to sign in our the Web3 auth gateway and the pending service. And how does the Crust help with the web hosting? Is there document guide tools on how to do web hosting on Crust network? Yeah, that's what I just showed, that you can integrate this into your GitHub workflow. Okay, let's say if this repository is your website repository, and then normally that you will check out the file when you're building the workflow, GitHub workflow. The first step may be check out the files, and then building using npm or using the yum command. And here you can use the upload action here to upload your build artifacts to the IPFS network, and then you ping the Crust network to make a store in the Crust storage nodes. After you will have the CID here in this step, right? When you get a CID, you can just open it on your browser. I can have let's see the compound finance, right? If you open its apps, okay, I think, let me check. Actually, it has a IPFS URL, but it isn't showing up here, I think. Anyway, so you just open the IPFS, just like how I retrieve the files here. If this file is a web file, then actually the website will be displayed in the browser. Okay, check. So that's it for the questions list. Okay, any other more questions?
You can go to the chat section if you want to. There are a few that discuss.
Okay, let me check. Oh, a long discussion list here.
Yes, from here.
Yeah, okay. Okay, just answer this question. Yeah, can we ping by the Crust network? Yeah, ping a file is persistent keep the file. Yes, that's right. Decentralized pinging. Yeah. Thanks, Ria, for the answer. And Connor here. Choose a POW, a POS, right? Both used here as different layers. Does that mean it takes lots of energy? Yes, still has POS potential weakness. Actually, this let me explain a little bit on the slides. Go back to this slides here, right? So as we just talk about that this layer is to prove how many files and how much storage are available on this node. I use the TE to send a report, and it broadcast report to the chain to tell the chain that, hey, I have 100 terabytes on my node, and I store like 10 terabytes of files on my node. And then the chain will verify that the report is valid, right? Then the GPOS here, we are relying on that storage proof report to calculate the staking limits. This staking limit is actually an incentivized mechanism to make the storage nodes to have more to have bigger storage resource and to store more files, because it can only have a higher staking limit if they have higher storage resource and have more files storing in that local node, right? So we are using the GPOS to make the whole chain have a consensus on all the node status. Well, actually, all the node storage power status, right? So we are using this GPOS to have this layer to make all the nodes have consistent and fair data across the chain. Okay. Yeah, using the CID, we can ping the crust. Does this have to be done on the Polkadot app? So it's just the easiest two. The other two, like a sticker lib. Okay, I already showed that, right? In the chapter 4, you can use any SDK, any tools you like to develop your application using the SDK or the IPFS gateway and pinning service. I just wonder why we just don't use SDC as a base covers or paying Web3. So, okay, I can answer this question because actually we are using the CID tokens in our network. And W5, okay, we answer the question. Purpose. Okay, it's meant to be used for nodes that are storing files. Okay, so it's doing a node calculation and checking. Okay, yep, answering the questions. Yeah, what APIs on Opponent that can interact with Crust Network? Yeah, I think Opponent will have another section, right, for this part. Okay, and is there a W3transfer Discord group? Maybe Yasin, you can answer this question, right?
Just give me a second. So we already have one, and you should already be in it. If you join the Discord, I'm gonna give you a quick link to join our Discord, and you will be able to pick the role, which will automatically add you to those programs group,
Yeah.
basically.
Join.
There it is. This is a bespoke Discord link. Once you join it, you will be on the upper right section. There's a roles button, and you just need to navigate to the WeTransfer Educate Series, where you can just, by clicking it, you will be added to the dedicated group, and you will be receiving all the needed announcements, tags, and so on for everything that you might be in need of.
Yep. Okay. Thanks, Jason. Does this work using a Polkadot wallet or talisman? I have to use these wallets. The Light AVM, you can use both, right? You can use Ether's wallets, also the Polkadot wallet or the talisman. That's fine. You can use all compatible EVM wallets and Polkadot wallets. Okay, the channel ID. Okay. Yep, I think I already finished all the questions. Jason?
Yeah, I think this was mostly it. Thank you, Brian. This was very thorough. A lot of useful recommendations and insights for everyone. Yes, thank you, Connor, and thank you all for being here for this live workshop. Again, all of the workshops are being recorded, so if you ever feel the need of going through some of them at once more or getting a deeper dive, we will be adding the recordings back into the Hacker Pack so that you can again rewatch everything. One final reminder. We do have a dedicated bounty associated with this Educate series, so do find yourself a team. You don't really have to, but it's always more interesting to find someone like-minded to build with. So get out of your comfort zone, say hi to someone, make a team, and hopefully build something for the bounty section that's associated with this Educate series, because there's 10K up for grabs. So yeah. that is it for this week, and see you all next one for the next workshop, which is going to be 3 out of 5. Thank you all. Have a great day wherever you are. And once again, thank you, Brian, for leading this amazing workshop.
Yeah, thank you. Thank you, everybody. Yep, goodbye.
See you. Have a great day, everyone.